The relevance of the Wigger's diagram to the clinicians, specifically those working in cardiac rehabilitation, is that you are superimposing some very important graphs over each other on an x-axis, on a common x-axis, that being time. So then you can see a cause and effect relationship between the many little systems that make up the greater cardiovascular system. This is very important, so then we can see if something's going wrong, what might be the cause. There's a lot of things that you can learn from that Wigger's diagram. And so the most central aspect of it would be pressure, but there's also left ventricle volume, EKG, ECG, the echocardiogram tracing, and the heart sounds, as well as the phases that it's going through. And you can see the difference between the diastole phase versus the systole phase. Now, when the heart starts in diastole, if we want to look at specifically pressure, I think the best example that you can give of the Wigger's diagram and what it can do is the aortic valve and the pressure that is in there, and how that relates to the left ventricle and the EKG tracing and the heart sounds. It ties it all together over a period of time. So, what am I talking about specifically? You can see that the aortic valve is currently at a pretty stable pressure when in diastole. But if we watch the EKG, we see the QRS complex, which we know to mean the depolarization of the ventricles. That means they're about to start contracting. And sure enough, directly after that QRS complex, you can see that we have an increase in pressure in the left ventricle, okay? And you can see that the aortic valve, the pressure remains stable because that valve has not opened yet. Why? Because the pressure is higher than that of the left ventricle, which is currently rising. And you can see that the left ventricle, the volume has remained the same because no blood has made it out of the ventricle yet. The blood is simply still in the left ventricle, and the heart is contracting, the ventricle is contracting, causing that pressure to rise. It's spiking very quickly over a very short period of time. And when it meets and overcomes the aortic valve's pressure, you see that it now opens the aortic valve and both of their pressures begin to rise because the ventricle is still contracting, but it's shooting blood out up into the aortic valve, and the aortic valve's pressure is now rising because there's much more blood in there. And now they both crest and they begin to stabilize because you can see that the left ventricle is running out of blood to shoot out, so the pressure has to continue to increase to get any more blood out, and then at some point there's no more blood it's going to give, and the contraction is beginning to end. And so the pressure begins to drop. And when the pressure drops below that of the aorta, the aortic valve will now close. And the left ventricle pressure will fall to the point where the mitral valve now opens, and we are fully in diastole here. And the atria are doing their job to fill the ventricles with blood now. How does this tie to everything down here? You can see that here at S1, that heart sound is being caused by that closing of the mitral valve, which is causing a sucking noise, causing the heart sound. And then further, if we look even further down here, we've got S2, S3. We're hearing the closing of that aortic valve at S2. That suction noise when that aortic valve is closing causes that loud S2 noise. So as you can see, you can watch through the diastole and the systole what is happening in the atria, in the ventricles, the pressure changes, the volume changes, why they are occurring together over a specific period of time. What's happening simultaneously, but more importantly, what's happening before and after an event to lead to that event and the importance of that event. What's happening electrically within the heart, and how is it sounding on a functional level? What are we hearing when we press the stethoscope to their chest?